Hello everyone, I am Rahul Shandilya and this is a video lecture series for Embedded System Lab. In this first lecture, video lecture, I will just give you about the introduction of what embedded system is, what platform we will use for the lab. So basically, what is embedded system? An embedded system is an electromechanical system designed to perform a specific function with real-time constraint and is a combination of both hardware and firmware. So the point to note is the important feature of embedded system is that it is to perform a specific function. While general purpose processor or general purpose computers has not defined any particular functions. Embedded systems are programmed for performing some tasks like in industrial, for example, even a keyboard has a particular some chips that interact with the main processor. So that chip has one defined function. Second important characteristic is that it is real-time constant. It has to perform in real-time constant. For example, in ATM machines, we have the time constant is very important. If there is a time delay or lag, the system can be faulty. So, and also we use the firmware software in this hardware so that we have better flexibility and controllability. So if we have to differentiate between general purpose computing system and embedded systems, basically we can see a general embedded system, general purpose systems has a full-fledged operating system, while embedded system operate on real-time R2S, real-time operating system. Then GPU, general purpose computing, execution behavior is not deterministic, while in embedded system execution behavior is deterministic, has to perform in real time. Again, response requirements are not time critical in general purpose computing, while it is very time constant in embedded system. So these are the few important applications of embedded systems. Consumer electronics like machine, microwave, home automation and security system, automotive, industry, telecom, healthcare, measurement and instrumentation, banking and retail, card readers, wearable devices. So we can see that embedded system basically is ubiquitous. Every electronic component we use, even the electric machine we use, or internet, everywhere in telecom, there are hidden small chips that continuously performing some particular task and enable us to function the largest system. And the latest is the Internet of Things. Internet of Things basically provide this embedded the chip here. Things is the smart things, which is basically the embedded devices. And Internet of Things basically is doing that. It is connecting these things with the internet. Earlier, only general purpose computer are connected with the internet. Now it is Internet of Things enables that every small chip, small chips or embedded devices can interact with another smart things that can place anywhere in the globe. So what are the main elements of the embedded system? Every embedded system has these few main elements. There is a processor. The processor can be a FPGA, ASIC, application specific IC, microprocessor, controller or system of chip, or some DSP chip even. Even though DSP chip it is not feasible that DSP chips have no memory to control. So, and then on this chip we have some memory in which we load embedded firmware to control it, to program it. And that essential important point is that it is connected with some larger system. The embedded system is always connected with some larger system. So there must be some communicating interfaces. We'll see various options for communication interfaces. And again, these most cases, these processors are connected with various sensors and actuators. So sensors are used to collect the data, while actuators are used to control some particular devices. Actuator example can be alarm, relay, while sensors can be say there are various sensors like lidar or photodiode. And additionally, we can add other devices, other interfacing devices to make it more powerful. So, what is the most important popular component of embedded system is the microcontroller. Microcontroller is basically a highly integrated chip that contains a CPU, computing unit, factored RAM, which is volatile, a special general purpose register array, chip or ROM to or flash memory. Flash memory can also act to load the program for the program. Timer and various other small functionality providing unit like timer, interrupt control, storage, and high port. So basically, Texas Instrument TMS 1000 is considered as the world's first microcontroller. Then Intel 85 is recognized as Intel's first microcontroller, and the most popular microcontroller by the Intel is 8051 family microcontroller. Then we have another company called Microchips, which brings the PIC family of microcontrollers, which become very popular. Basically, the PIC microchip based PIC based family are RISC microcontroller against the CISC architecture of the 8051 from the Intel. So, RISC is basically reduced instruction set computing, while CISC stands for complex instruction set computing. RISC we have a smaller number of command assembly code, while it's opcode, while in CISC we have large number of code. And also there is another popular microcontroller family is AVR from the Atmel. So AVR brings flash memory for storing the program, and that's why it was very easy and flexible to program these devices. Arduino is the example. In Arduino board we have AVR microcontroller, Atmel microcontroller. Now recently Atmel is basically purchased by Microchip. So Microchip support both the PIC family and the AVR family. So what is the difference between microcontroller and microprocessor? It is basically same as general purpose computer or say embedded system. In microprocessor we have a CPU, and we have to connect additionally hard disks. We have to connect additionally RAM. Every network interface card we have to connect externally. While in microcontroller, in the same board, these components come. Basically, for interfacing device like SPI, I2C, RAM, EEPROM to load the memory, or a small RAM. So these are on the same board. That is the biggest difference. And also, most of the microprocessors are basically Harvard architecture, while microcontroller is based on Princeton or von Neumann architecture. In Harvard architecture, there is a different bus for data and instruction. In von Neumann architecture or Princeton architecture, there is only single bus both for instruction and data. So this is the biggest difference. And also we in microcontroller has many GPIO port, while microprocessor has no GPIO input, general input output port. We have to attach some interfacing device for that. Microcontroller is cheaper and they save consume less power, while microprocessor consumes uh, more power. CISC and RISC architecture difference is also very popular. RISC is, as I said, reduced instruction set computing, while CISC is say complex instruction set computing. RISC instruction pipeline and increase execution speed. There is no instructions in pipelining features in the CISC architecture. On the RISC, operations are performed on register only. The only memory operations are load and store. Operations are in CISC, operations are performed on register or memory depending on the instruction. In RISC, a large number of registers are available, while in CISC, limited number of general purpose registers. In RISC, programmer needs to write more code to execute. As we have less number of instructions in the RISC architecture, we have to write longer code. In CISC architecture, as we have larger number of code, say instruction, so we have to write less code. Again, because there is less number of instructions, RISC architecture is basically simpler than the CISC architecture. And mostly CISC, as I said, is deploy Harvard architecture, while CISC can have both Harvard or von Neumann architecture. While CISC microcontroller have basically the von Neumann architecture. CISC microprocessor is basically a CISC architecture, and it has a Harvard. Now come to the communication interfacing, which is very important for the embedded system. A single chip is good for nothing, so it has to communicate with other chip or another microcontroller. It has to communicate with something. For that, there are some communication protocol for embedded system. The most popular one is the I2C, SPI, and UART. I2C or I2C is basically I2C, IC to IC communication. It has only two bus, basically two wire for communication. It is say synchronous because one bus is basically as here in this diagram you can see one bus is SCM, which is stand for synchronous clock, and another is SDA, which is stand for synchronous data. So on one wire clock signal is passed, on another wire data is passed. So these clock signal basically synchronize the data between various IC. So various IC are connected in master slave mode. Means one IC is master, which controls this clock signal, while other IC act as a slave. They basically use to send and receive data. As it is there is only one wire for data, therefore it is a half duplex communication protocol. That means at a time data flow in one direction. Means at a time data flow can from master to slave or slave to master, not both at same time. While SPI is another protocol, which is a full duplex protocol, and we have two wire for data, that is MOSI, master output, slave input, and MISO, that is master input and slave output. And then we have one wire for clock and another wire for chip select. Basically it is used to select which slave is used for communication. So in SPI only one pair of master and slave is connected at a time, but multiple number of slave can be connected in different time, which is enabled by this chip select pin. And the third is we have UART. It is asynchronous form of transmission, where two wire basically transmitter is connected to the receiver of another device and receiver is the transmitter of another device. It is asynchronous, so the different parameters like the flow control, baud rate, signal level are predefined, and based on that predefined parameter the data is ensured that the data will communicate or pass safely or correctly without any error. The error can occur, therefore we have some redundant bit to check that error. So we have basically three more popular microcontroller. One is 8051 architecture, another is a PIC architecture. In 8051 architecture, we can see various components of the microcontroller UART for the communication, RAM to store the volatile means ROM to store the memory instructions, and RAM while in operation the instructions pass into the RAM. CPU timing and control unit. Then we have various registers. Similarly, we have Microsoft PIC architectures and then AVR architecture. So basically, in this diagram, you can see the basic simple uh, instruction set, how load and store instruction set work in the microcontroller. Basically, program is stored in the register. Here, instruction and data is also stored on the register. Instruction data is stored in the register. It is connected to various registers. So X is connected to R1. So for example, when I say load R1 X, that means X is loaded to R1 register. In second instruction, we have load R2Y. This Y is basically loaded into R2 register, and then we have instruction add R1 R2, and the resultant is stored in R3, and R3 is connected again to the Z. Therefore, the result is stored in this. So in this way, load and store instruction is carried out in sequence and perform all the functionality. So for this is the basic introduction of the embedded systems. In this lab, we will perform various. There are almost 10 experiments, and we will adopt PIC group of family micro, which is from Microchip, to perform all these experiments, and we will use MPLAB IDE, that is integrated development environment, to simulate the PIC microcontroller. That's the end of this lecture. We'll meet in the lecture.